So before moving towards really the bigger question of the bigger picture of the topology as promised in previous video, I would like to quickly expand over a question actually. And that question will allow us to basically understand really the beginning of the topology, how the topology was born actually. Okay, and the question is this: what is the meaning of making an idea, a concept, or maybe a notion, and making it mathematically rigorous? Okay, making it mathematically rigorous. Okay, so you quite often hear in mathematics that maybe like there are things in mathematics which are not mathematically rigorous. They are being used, okay, and there are things in mathematics which are mathematically rigorous actually. So what do you mean by turning an idea, concept, and notion into mathematical rigorous actually? And really the answer is very simple. Okay, to make an idea rigorous, can you express that idea, okay, or concept, notion, whatever, can you express it precisely in the terms of sets or functions actually? Or in fact basically functions are also sets. So really if you want to make an idea, concept, or notion mathematically rigorous, can you express it in the terms of a sets actually? So if you can express an idea in the terms of sets, we will say that we have made that idea mathematically rigorous. So let me illustrate this through an example actually. That let's take something that is not rigorous, but how we can take the same thing, and if we can express that in the terms of sets, will become rigorous actually. Okay, so let's just start with something, for example, elementary. So everyone knows that what is dy by dx actually. Okay, so we all know that, like, we are computing the derivative of the y with respect to x. In other words, that you may interpret that, like this dy by dx is really the rate, in a rate of change in y when x is changing actually. But if you ask from yourself that what is really meaning of dy and what is really meaning of dx, what are the precise meaning of dy and dx, quite often the answer that you will get is that like this is a fancy way to say it as that, like, this is the infinitesimal change in y, and like this guy is really the infinitesimal change in, so it's like infinitesimal change in x. And then you are tempted to interpret that, basically what you are doing here is that you are taking this infinitesimal change in y and taking this infinitesimal change in x, and you are taking the ratio of it actually. So the derivative is really the ratio between the infinitesimal change in y and the infinitesimal change in x actually. But the trouble is that this ratio would make sense if we can make sense first that what do you mean by infinitesimal change in y and what do you mean by infinitesimal change in x actually. So a common way to say that, what is the meaning of infinitesimal change in y is really think of something smallest okay, in your head actually. So think of something smallest. Okay, so some people can, think of say atoms, and maybe some people can think of electrons, and maybe some people can think of quarks. Okay, or maybe if you're a string theorist, you can think of strings actually. That okay, really these are the smallest kind of objects with the smallest possible size. So when you are saying that okay, like this dy is a small change in y, like, and it's an infinitesimal change in y, it's really the smaller even than the atoms or electrons or quarks or anything that you can imagine, so smallest actually. But this already tells you that like that's not a precise way of describing dy actually. So if like you will always ask, if something is small, how small? You can, someone would say you really, really, really small, but how much really, really, really small actually? Okay, so so the trouble is that like this dy is not mathematically rigorous. Okay, it's like it can't be precisely described. Similarly, dx is also not mathematically, what do you call, rigorous actually. So it's like neither dy is precise and neither dx is precise. Then how come the ratio of both of these quantity would be precise? Okay, Sir Isaac Newton coined basically this notion of a derivative, or also Leibniz at the same time. Okay, but their description was not precise. Their description of like this derivative was intuitive actually. Okay, it was intuitive, not precise. Okay, but if you want to make, for example, this notion precise, how can I make it precise? So one way, or maybe the rescue of this comes from something which is called the linear algebra. Okay, so we can treat this d by dx as a linear transformation. Okay, so it's a linear map actually. It's a linear transformation. Okay, if you treat d by dx as a linear transformation, that swallows a function y and it spits out another function, what do you call, dy by dx. Okay, now treating d by dx as a linear transformation is a rigorous notion actually. Okay, because every linear transformation is basically a function, and every function is a set actually. So I know now precisely that what is the meaning of dy by dx. I would say that okay, I have a operator d by dx which is operating onto, what do you call, y. Okay, so in other words, the entire theory of linear algebra is sitting behind this notion of dy by dx. So if you treat dy by dx as, say, the ratio of infinitesimal, it's not rigorous. But if you treat d by dx as a linear transformation, for example, it's rigorous actually. I hope that everyone of all of you must have taken, for example, the first course on linear algebra, and you must have seen the derivative d by dx as a linear transformation.